In Chapter 5, we talked about discrete probability distributions. So Chapter 6 is all about continuous probability distributions. Remember the difference between a discrete variable and a continuous variable is basically a discrete variable is anything that can be an integer. You know, things like number of friends, number of customers, number of takeoffs, number of customer service calls. Whereas continuous, now we're moving to things like sales, revenue, market share, profit, weight, GPA, things that can have a fractional value. So students and cars, that would be discrete. This chapter we're focused on continuous, so things like weight, GPA, sales, revenue. So a few examples, weigh 100 people, so the weight in kilograms might follow a continuous random distribution. Measure life of a part, maybe a cell phone component or part, in hours. Or maybe you give a survey about the amount spent on food. Measure time between customer arrivals. This is a big one. Measuring time between customer arrivals or how long it takes to service a customer, let's say at a bank or something. Whereas we saw with the Poisson distribution in the last chapter, we were focused on the number of customers, something discrete. In this chapter, we'll focus on the time between customers, so something continuous. Okay, a few things to note for this chapter. We're going to be focused on intervals instead of integers. So in the past, we were focused on the probability of 0 plus the probability of 1 plus the probability of 2. Here, we're more concerned with intervals. What's the probability of having between 300 calories and 400 calories? What's the probability of customers waiting between 10 and 25 minutes? So you can have decimal or fractional values because we are talking about continuous variables now. So exact point probabilities will be equal to 0 in this chapter. So if I'm talking about cell phone minutes, the exact point probability of, let's say, 10.2 minutes is going to be equal to 0. Because we have fractional values, it's really 10.2009652 or something like that. So being exactly equal to that is 0. Okay, so if x is continuous, then the probability that x equals 10.2 equals 0, which is going to be helpful because when we're doing our Excel functions, we don't need to worry about exactly equal to. So, you know, when we did the cumulative part of the Excel functions for Poisson, you know, we had to worry about whether we say true or false for the cumulative. In this chapter, we'll only say true because false was for exact point probabilities. But you'll see that when we go through a few examples. So probabilities are actually areas under the curve. So for example, for the discrete variables defined at each point, we would talk about probability of 52 plus the probability of 53 plus the probability of 54. Whereas in Chapter 7, where we're concerned with continuous variables, we want to think about intervals, and probabilities are areas under the curve. Okay, so let's look at some examples. Let's start with the normal distribution. We won't cover uniform distribution because it's really not that likely in business. It would basically say that every value of x, say time, is equally likely. Well, that's pretty uncommon in business for all times to be equally likely, like 10 minutes to be just as likely as 85 minutes. So we'll just jump to normal distribution. They're measured on a continuous scale. You know, discrete versus continuous. Chapter 7 is all about continuous. They possess a clear central tendency, so you may recall that normal distributions follow a bell-shaped curve, so there is a clear central tendency in the top of that bell. Only one peak, so it's unimodal, and they exhibit tapering tails, so something like the amount of caffeine in a Starbucks mocha. All are going to have pretty similar to the same amount of caffeine because there's a specific recipe, and you want your baristas to be consistent with how they make it. But there will be a few variations, some with a little bit more caffeine, some with a little bit less. And for normal distributions, they are symmetric about the mean, so there's equal tails. So some examples here. Diameter of golf balls. Anytime there's something like a machine making something, you're typically expecting most, in this case, fall around 42.7 because that's the mean. But there will be a few that are a little bit more and a few that are a little bit less. Same as these CPA exam scores here, probably Typically, you wouldn't have CPA exam scores following a normal distribution, but in this case they did. So just a thing to note is basically what Excel is doing for us is standardizing every X value. So if a golf ball has a diameter of 42.69, it's going to convert that into number of standard deviations, and then I can use the empirical rule where I know probabilities under the curve. But Excel's going to find those probabilities for us. Okay, things that tend to follow a normal distribution. Amount of Diet Coke in a 2-liter bottle. Because it's using a machine, most are going to have exactly 2 liters, but of course there's going to be a little bit of variation, some with a tiny bit more, some with a tiny bit less. Amount of cockpit noise in a 747, or amount of caffeine in a Starbucks coffee like I mentioned. So you have that central tendency where most are around that central tendency, and then a few on either end in the tails. Okay, so let's jump into an example. Let's say an Egg McMuffin calories is a normal distribution with a mean of 290 calories and a standard deviation of 14. What is the probability that an Egg McMuffin has less than 300 calories? So I'm going to go to Excel and use the normal distribution function. Okay, so equals norm.dist, and then the X that I'm interested in. I wanted to know the probability of fewer than 300 calories. So I want to put 300. The mean was 290 calories and the standard deviation was 14. And now remember in chapter 7, there's not really a need to put false here because I don't want exactly equal to 300 calories. I know that exactly equal to 300 calories is 0 because exact point probabilities are just 0. So I would never want to be finding that. So 76.2% chance. Okay, how about more than 250 calories? Remember, for greater than problems, I'm going to need the 1 minus, the complement rule, because Excel is giving me the cumulative, so that's basically for less than problems. You know, if I'm plugging in 250 and it's giving me the cumulative, it's giving me the probability of everything up to 250. So that's basically a less than problem, 250 or anything lower than it. Okay, so in this case I want to do 1 minus the probability and use 250. So normal distribution, 250, the mean is 290, standard deviation is 14, and we want to say true. And then just don't forget to put the 1 minus. You can do it at the end, but putting it up front makes it a little easier to forget, or a little harder to forget. So 99.78% chance of an Egg McMuffin having more than 250 calories. So you can imagine, like, if I'm a manager, I can test out a bunch of these different combinations and see if I should be worried. You know, if a lot of them are less than 250, maybe there's certain ingredients being left off. If a lot of Egg McMuffins are more than 300, maybe people are adding too much cheese or ham or something like that. And I want it to be consistent, so I need to talk to my staff or maybe make sure the rules are a little bit more consistent. What about between 275 and 310? Anytime I have a between like this, I basically just take the less than for 310 and the less than for 275 and subtract them to get the in between. Okay? So basically, for the 300, less than 300, you can see there what I did and got the 76%. 76% chance that a customer will get an Egg McMuffin less than 300 calories. More than 250. Again, I use the complement rule for greater than problems. 99% chance. And then for between problems, like I said, just treat them both as less than and subtract the lower one from the higher one. So in this case, start with the 275 calories. You can start with the 310 as well, but just make sure to subtract the lower one from the higher one. 290 was the mean, 14 was the standard deviation, and I'm always going to say true for cumulative in this chapter because exact point probabilities are 0. Okay, do the same thing for 310 calories, and then just subtract them. Okay, so 92.3% minus 14.2%. And you get 78% chance that the calories will be between 275 and 310. Okay, so as a manager, I don't have concerns. If the probability of an Egg McMuffin having over 300 calories was high, I'd be concerned. Talk to my staff. Maybe they're putting too much on. If the probability of less than 270 was high, I'd also be concerned. Maybe they're leaving off things that they should be putting in there. Okay, another example. HDTVs. Lifetimes of a particular brand have been found to be normally distributed. Average lifetime is 5 years, so the mean is 5, with a standard deviation of 2. What is the probability of TVs failing in less than 4 years? So you can imagine, as a manager, I would want to know that. If they're failing pretty often, under the average lifetime of 5 years. Okay, so I was told that it's a normal distribution. I want to know probability of failing in less than 4 years when the mean is 5 and the standard deviation is 2. Okay. It's a less than problem, so I don't need the 1 minus, but I am going to do the cumulative. So 30.8% chance of failing in less than 4 years. Okay. 31% chance of failing in less than 4 years. As a manager, I'm not really comfortable with that. So if I'm the manufacturer, I need to find a way to make better TVs, or talk to some people, find out what the machines are doing. If I sell that TV, I might consider not selling it anymore. Not going through that company that makes that TV. Okay, what percentage of the population of all HD TVs will have a lifespan between 3.8 and 22 years? So another in-between problem. We take the less than for the 22, take the less than for the 3.8, and then subtract them. Again, the mean is still 5, and the standard deviation in this case is 10. Okay, so if we take a look, probability of being between 3.8 and 22 is just take the probability of less than or equal to 22 and then subtract the probability of less than or equal to 3.8. You get 0.9554 minus 0.4522 for a probability of about 50%. So in Excel, you can see there you just use the norm distribution function for the two values and subtract them.